All right, this will be an introduction to solving projectile motion problems. So let's start out and just talk about what projectile is. A projectile is any object that's acted upon only by the force due to gravity. So we neglect air resistance, we neglect any other force that might interfere with it, and we assume that the only force acting on it is a force due to gravity. So to start getting ready for solving these types of problems, let's take this example here where a car, this is a car, is suspended by a cable or something 10 meters above the ground. And say someone comes along and they cut this cable. Well, what do we know? In this problem, what would we know? I would know the initial velocity of the car. How fast was the car going at the instant they cut the cable? And the answer would be 0. So I would know this car started out traveling 0 meters per second. I'm going to say initial velocity in the y direction. We haven't been doing that yet, but we're going to see that notation can be helpful for us in terms of keeping our variables straight when we solve problems like this. Really being explicit about what's going on in the y direction or in the vertical versus the x direction in the horizontal. What else do I know about this? Well, this is just a free fall problem, right? And anytime an object's in free fall, I always know acceleration. Acceleration is always down, and in a free fall problem, it is always equal to g, which is 9.8 meters per second every second. What else do I know? Well, when they cut that cable, what's this car going to do? It's going to go down 10 meters. This is its starting point. It's going to end somewhere down here. And the direction of travel for this thing, the direction of its displacement, is downward. So I know displacement is going to be downward. Instead of writing delta x, I'm going to write delta y. It's the same thing. You can use them interchangeably in equations. When you solve problems for me, you don't have to say delta y. You can say delta x. I don't care. But it might be easier for you, and you might see it written as delta y when it's a vertical displacement. I know delta y is down, and again, I'm putting my arrows over here so that I can be consistent in giving algebraic signs to these things. If I have vectors pointing in opposite directions, I want to make sure they have opposite algebraic signs. In this case, they both point down, so I don't need to make them negative. I just need to make sure they both have the same sign. I can leave them both positive. I know that is 10 meters. Now, do I know anything else for sure at the beginning of this problem? No, I don't. But can I find things out? Sure. Can I find out the final velocity in the y direction? Yes. What is this thing going to do? It's going to start out at rest. Let me write these arrows over here. And it's going to be speeding up. And every second, its speed's going to increase by 9.8 meters per second. That's what that means. The acceleration means. And I can find out how fast this thing will be going the instant it hits the ground. We can do that calculation. We have an equation that will let us figure that out. I can also find out how long it's going to take to hit the ground. How long will it take for this thing once it's dropped to hit the ground? So not a problem. You should be at a point now where you're able to do that. Let's look at another type of problem. Let's look at a constant velocity problem. We did these a long time ago. So this should be no problem for you. Let's say that we have a car that is traveling at some velocity along the horizontal, and we know it goes 50 meters. And I know it's traveling at some horizontal velocity, and I'm going to put a little subscript of an x there to remind myself that it's a horizontal velocity. Well, what can I find out about this? What do I know that's going on in the x direction? It has some x velocity. I know that delta x is 50 meters. And really, I cannot find out what the velocity is unless I know one other variable. In a constant velocity question, this equation can be applied, and I can't find its velocity unless I know the time. But if I gave you the time on this, if I said, hey, this whole event took 1.4 seconds. It took 1.4 seconds for this car to go 50 meters. Then could you find the velocity? Sure. You could say, well, I know the velocity. You just plug in your numbers. It went 50 meters in 1.4 seconds. And when you put that in your calculator, you could find out its velocity, and that would be constant. So if I wanted to draw that out, I could say that it was going at the same velocity. I would draw the same length arrow. indicating that it was at the same velocity, as opposed to these where the arrows get longer and longer and longer, showing that the velocity is getting larger. So why do I bring this up? These are two things you know how to do. These are two things you've been doing. So let's say I give you this problem. Where I have a car that goes off a cliff at some velocity, and it falls 10 meters, and it lands 50 meters from the edge of the cliff. And I want to know, well, how fast was it going? Which actually I already told you how fast it was going. I ruined the suspense here, but I won't the next time, I promise. It's going to follow a path that looks like this. It's going to follow a parabola. Why is it going to follow a path that looks like that? Because along the horizontal, it's going to be moving at this constant velocity, x, whatever it is. That's the unknown in this question. But along the vertical, it's going to start out at rest, and it's going to pick up speed as it falls. Because it is accelerating, it is in free fall vertically, and it is at a constant velocity horizontally. And that's a little unintuitive, maybe, that the horizontal velocity wouldn't be affected, this blue vector that I've drawn here, this blue arrow. But think about it. If we're neglecting air resistance, what force would there be to change the velocity of this car? There's no force acting on it at all along the horizontal. And in fact, the only force acting on this car is gravity. If I were to draw a free body diagram for this car, or a sort of free body diagram, if I were to indicate what forces are acting on this car, the only force would be the force due to gravity, or the weight. The force that the Earth is exerting on this car. That's all that's acting on it, and it's acting downward. There's no horizontal force, so there's no horizontal acceleration. So we see that these vectors, the green ones, the vertical ones, get bigger and bigger and bigger. The velocity gets bigger and bigger and bigger. It's in free fall. And the blue ones stay at a constant velocity. That shows that it's at a constant velocity along the horizontal. So if I wanted to know, if I gave you this question and I said, well, how fast is it going along the horizontal? The instant it goes off this cliff, it goes at that same speed during the whole trip down. You could find that out. And the first thing we would need to do is set up our variables and find out, well, what's going on in the y direction and what's going on in the x direction. And we've already done that. I'll just rewrite it over here, but all I'm going to do is rewrite what's in white here and what's in, well, kind of what's in yellow here, this part. So along the horizontal, I put CV here just to remind myself this is at a constant velocity. And that means that this is the equation that I'm going to use. I can use any of the other kinematics equations if it floats my boat, right? But when acceleration is 0, it would end up boiling down to this equation anyway, because acceleration would drop out of any term with acceleration, and it would drop out of those other kinematics equations. So I'm going to use this one. What do I know about the horizontal? Well, I know the unknown is the velocity along the horizontal. That's what I'm trying to find out. This 50 meters, I'm going to call delta x. Why? Because it's horizontal. Just like in a graph axis, the x-axis is horizontal. I'm going to call this delta x. It's 50 meters. And what else do I know about the horizontal? I don't know anything. But when we look at this equation, what else is there to know? The only thing is time. And that's not a vector. So that wouldn't necessarily be attributed just to the x direction or y direction. Time is scalar. What do I know that's going on in the y direction? I'm going to put that this is in free fall in parentheses just to remind myself that this is accelerating due to gravity. So the first variable I'm going to write down is acceleration is g, and it's 9.8 meters per second downward. I'm just rewriting these variables. I know that it's going to fall downward 10 meters, right? It starts up here and it ends down here, and that displacement, forget about that it moved horizontally, that displacement is 10 meters. So I know that it fell 10 meters down. And I also know that in the y direction, it started at 0 meters per second. Just like in this case here, it started at 0. This velocity, when it was on the cliff, The instant it went off the cliff, it was not moving downward. It was not moving upward. It was moving with this horizontal velocity, whatever it is. That's my unknown. In the y direction along the vertical, it wasn't moving at all. So it had no velocity in that direction. Now I have this set up, and I need to find out, well, what variable do these two columns have in common? What variable belongs in both the x column and has the same magnitude in the y column, and that is time. The amount of time it took this thing to drop down these 10 meters is exactly the same as the amount of time it took this thing to move across 50 meters. This event began when the car left the cliff, and it ended when the car landed at the bottom here. And that was the same along the horizontal and vertical. Time is the variable that belongs to both columns. So if I can solve for time, I can use either data set. I can use my y information to find time or my x information to find time. But if I can find time, I can solve this problem. So can I find time with the x information? No. We see that time is in here. In order to know time, this equation has three variables. This is my equation that I'm going to use when I have constant velocity. I would need to know velocity, and I would need to know delta x. And I don't. Velocity is my unknown. So I can't use this to find time. But is there a kinematics equation that I can use that will let me find time when I know acceleration, displacement, and initial velocity? And there is. So which of my equations has displacement, initial velocity, acceleration, and time? And it is this one that we seem to use all the time. Let me actually write it the way that we learned it. Delta x equals v naught t plus 1/2 at squared. And you can use this. Again, on a test or quiz, I don't care. This is fine. You can use this. I'm going to write it, instead of delta x, I'm going to write delta y, just to indicate that this is a vertical axis variable that I'm talking about. Excuse me. Delta y, this vertical displacement instead of a horizontal displacement. I don't care what you do. I'm going to put v naught y t, and again, because I'm dealing with two sets of variables, I'm dealing with horizontal variables and vertical, and just in the problem, when I look at this work, when I look back at this work, I want to know what I'm looking at. Plus 1/2, and instead of a, I'll write g. It is the acceleration, right? The acceleration in a free fall problem is acceleration due to gravity times t squared. So if I want to use this to solve for time, what we have been doing, and this will be another case of that, is we've been getting rid of this term because v naught is 0. If this is 0, 0 times any number is 0, and 0 plus any number is that number, right? So this would end up with 0 plus 1/2 gt squared. I can just get rid of this term. So I end up with delta y is 1/2 gt squared. If I want to solve for t, I need to isolate it. I can, to get rid of 1/2 on this side, I can multiply both sides by 2. Let me get a different color here. This would be 1, right? 2 over 2 is 1. But I'd have to multiply this side by 2. I would end up with 2 delta y equals gt squared. I want to isolate t, so I'm going to divide out g from both sides. G over g is 1. I end up with 1 times t squared, but I don't have to write the 1 in. So I end up with 2 delta y over g equals t squared. I don't want to know what t squared is. I want to know what t is. So I took the square root of both sides. I end up with t equals the square root of 2 delta y over g. Now I'm going to substitute 2 times. Make sure you put in delta y. This is why it is helpful to call it delta y and not delta x. You might just glance over here and use the 50, but remember delta y is 10. So this is what you're solving for using these variables along the vertical to solve for this. So make sure you use the y displacement, the vertical displacement. 2 times 10 over 9.8 meters per second squared. And when I solve for that, I get 1.4 seconds. Now that I know time, the sole purpose of this problem was to find out how fast it's going off the cliff. Now that I know time, I can find that. This is a constant velocity. So remember, The equation that I'm going to use is velocity is displacement over time. The displacement's 50 meters, and the time is 1.4 seconds, and so this car went off the cliff with a velocity of 33 meters per second. So that is the answer to this question.